Happy students, welcome to this quick and focused review of Unit 2, Differentiation, the definition and fundamental properties. So I will be covering the key concept and the techniques you need to know. So let's dive in and get started. So first subunit, defining average and instantaneous rate of change at a point. First, what is average rate of change? We know speed is distance over time, right? This is a change actually over a time, how much distance you have traveled. That is the speed. So it's a basic. In the function form, when you are getting into derivatives, we have a graph here, and you take 2 points. First point at x is equal to a, and the next point is x is b. So average rate of change is change in y by change in x. That's simple. So change in y is f of b minus f of a, and change in x is just b minus a. So it's very usual thing that we have been dealing so far. Now, coming to instantaneous rate of change at a point. So we won't be given 2 points here. At x is equal to a, what's the change? We need the instantaneous speed or instantaneous change. So for that, we have only 1 point, right? So we will be taking another point, and that point should be infinitely close, like it's very, very close to the given point. So I made an expression, that point is over here. If we take, it's a plus h, comma, f of a plus h. And now you apply f of, it's same thing, right? So they are very close, but still they are two distinct points. This is the thing we have taken. So, and if you apply the rate of change is change in y, f of a plus h minus f of a, and then you will get something like a plus h minus a. When you simplify, the denominator will go just h, right? So if this h is infinitely small, like it's like 0 point, like 1,000 zeros, lakhs of zeros, millions of zeros followed by 1, that is infinitely small, but still it's a distinct point, right? This one, and so 3 and 3.001, they're very close, but they are still distinct. So this is the instantaneous rate of change at a point concept. It's still a quotient looks like this, but your h is infinitely small. Let me explain this with the help of a platform over here, and here we go. Okay, so there is a function given, right? F of x is x square. Now we have 2 points, so a is like this, and your h, if you make it 2, let me remove this. So this is a secant line. So secant line means what? It crosses the graph at 2 points, 2 distinct points. So this is when I take a is like -3 and b is as I'm just adding 1, -1. So I got a secant line. This, in this case, like it represents average rate of change, right? So you will get an equation of secant line. But for instantaneous, I need a tangent because at one point the line should cross. So I have to make the h very, very close to the a. So I will be reducing my h. And when I put 0, it will eventually become a single point and I will get a tangent line, right? So this is the concept. A secant line will represent average. A tangent line will represent instantaneous rate of change. And moving to the board. So quotient express average rate of change over an interval. This we have seen, right? Actually, I have used BA. So instead B, you just A plus H. What if your H is 3 and A is 2, right? So A plus H minus F of A by A plus H minus A. This is for a point. Generally, for a function, you can replace that second value with X. This represents slope of a secant line. Now coming to instantaneous range, you just apply limit H tends to 0. The same expression, but I'm trying to make that h infinitely small, which is in limit form h tends to 0. Or this way we can do. So this quotient will represent, this expression will give you slope of tangent line. And that's all about the instantaneous and average rate of change. Now, second subunit is defining the derivative of a function and using derivative notation. Okay, what is this derivative? It is also an expression. Like function is an expression, derivative is also an expression. This will help us to calculate instantaneous rate of change, right? That is a new thing we have learned. It won't help us in calculating average. It will help us in calculating instantaneous rate of change. That means what graphically? Slope of tangent line for a given function at any given x value. So simply, if you want a slope of a curve at a point, you just derivative. You find the derivative and that's simple, and plug in whatever value you're looking for. That's simple. This is the derivative definition. It's nothing but instantaneous rate of change. Now we have f of x expression, f dash of x, and this is the graph, right? So if you want the rate of change at x is equal to 0, it seems like a horizontal line. So there is no change actually. So in your f dash expression, just plug in 0 because you need a slope. You need the instantaneous rate at 0. So plug in 0 and you will get 0. If you want instantaneous at rate at 1, yes, there is a kind of increasing rate. So we'll get some positive answer here and you just plug in, you will get exactly the answer. So instantaneous rate of change, if you have the expression, you can get it exactly wherever you're looking for in a graph. And if you wanted 3, I can't see it in the graph, but still this expression will help me. So f dash of 3, the slope at 3 will be 6. That's simple. Now, graphically, how can I do? F dash of 0 means you are trying to draw a slope or you are trying to find slope of the tangent. So at x is equal to 0, draw a tangent. It's a horizontal line. Horizontal line will always have 0 slope. So you don't want expression every time. If you have a graph, you can evaluate it. And f dash of 1, you just draw a tangent at 1 and apply the slope formula. We know slope of a linear function, right? Rise over run. Rise is 2, run is 1, 2 over 1 is 2. So this is what we actually get with expression. Without expression, using graph also, we can still get the same, right? We have a lot more techniques. And coming to notation part, we have two main notation, Lagrange notation, which is if f of x is your function expression, then first the derivative is f dash of x, the prime notation. And if you note it with y, it's y dash. This is common. And Leibniz notation, if you note it with y as a function of x, then the derivative is dy by dx. We are differentiating y, or we are finding derivative of y with respect to x. This is what Leibniz notation means. Simple. Now, definition of derivative is a limit expression which looks like this. F dash of x is limit h tends to 0, f of x plus h minus f of x by h. Right? This is what we did. Instantaneous rate change, right? And one quick example, find the derivative using definition for this. So first you write the definition, then, okay, h tends to 0. You have to find the numerator expression f of x, if x square, f of x plus h is x plus h the whole square. Then you have to apply, just plug in the expressions. We did that and expand this and simplify it. So h will get cancelled and limit h tends to 0. The simplified expression is this. Now you plug in h is 0 and you will get 2x. So you see f of x is x squared and f dash of x is 2x. This is using definition of derivatives. Now, one more important thing, we are talking a lot about tangent line when it comes to derivative, right? So how to find equation of tangent line? We know how to find equation of line at when one slope, like 1 point and slope is given. So this is slope point form. The same thing we're going to apply in a modified version. So y is y minus y1. Because I'm finding equation of a tangent line at x is equal to a. So if your function is f of x, that point, the coordinate will be a comma f of a. y1 is that f of a. So f of a equals slope is, how will you find slope of a function? You have to find derivative and then plug in whichever point you are calculating the slope. So f dash of a will be the slope expression and x minus which point we are solving, the x coordinate is a. This will give you equation of tangent line. Simple. And estimating derivative of a function at a point. So here they have given a function which is little more complicated. We need to find the slope at 2. F dash of 2 means slope of f of x at x is equal to 2 with technology. So this is using analytical method, using TI-84, and this is using Desmos. You can graphically solve this also. So let me teach you both the ways. And here I'm sharing the screen. Okay, first analytical way is, so you can just open a calculator page and then you can go for menu. We are doing calculus and it will have some list numerical derivative at a point. Click on it. And your variable is x. Even if you're dealing with theta, just interpret as x here. And value we are focusing is x is equal to 2. So the slope, where you want to find the slope at 2. And first derivative. So that's it. Then you will get something like this and just plug in your function. And it's very important, sine, whenever you give input, use the parenthesis sine of cos x, right? So cos is an input and x is an input for cos. So the parenthesis is important, otherwise it will show some error. That's it. We have calculated it analytically. In TI-84 also, you can graphically do this. But you can use Desmos also, right? In your AP exam. So let me show that to you. So this is for a derivative at a point. So very simple. First you define the function as f of x and you got a function. But I need derivative. So just use the notation, Lagrange notation, right? F dash. And that black graph you can see here is derivative. So it's very simple. You need f dash of 2, right? So you can just plug in, it will give you, or you can graphically like at 2 what the black color graph represent. So it represents this, right? Or you can do something like this, x is equal to 2. So we have a lot more ways to find that. We got a same answer graphically and analytically using technology, right? Okay, and moving forward. So we have been solving this and we got the same answer. Now, estimating derivative of a function at a point without technology. Without technology, like they will give you some table values here. So it's very simple. First of all, if the derivative exists, f must be differentiable and the graph should be continuous and smooth if it's a graph or a table form. So that is obvious condition that have been applied and then we will be solving. So there is list of values and we have to estimate f dash of 5, right? So 5 lies between 4 and 6. Actually, 5 lies between 0 and 8 also. But you have to pick a best interval and that's 4 and 6. So just apply average rate of change for this and f of 6 minus f of 4 by 6 minus 4. That's the best we can do here. And again, it's just estimating. It won't be the best, right? With this information, this is the best instantaneous or derivative of a function. And it's approximately 1, right? This is using tables. Next, we are in 4th unit, connecting differentiability and continuity. So in this case, we learned continuous in our previous chapter, right? It's smooth, you won't take the pen, there will be no, like, without lifting the pen, you can smoothly draw a function. And differentiability have one more extra stuff. So, and also this will tell us if it's differentiable, a derivative will exist there. If it's not differentiable, it won't exist. So let's understand this one. So continuity we know. So what is this differentiability? So it's very simple. Graphically, if you want to visualize, if you zoom in at a particular point, zoom in, like you zoom in how much you can do. And if it tends to become look like a straight line, then it is differentiable. Yeah, I'm zooming at a point, but it doesn't show straight line, some gap or some blank. Something it shows means it's not becoming a straight line when you zoom in, then it's not differentiable. That simple it is. But so here you see this is a differentiable function. First of all, it should be continuous. So that's the thing. And yeah, it's continuous. Is it differentiable at x is equal to 1? So you don't zoom in here. On the graph, you have to zoom in. Okay, don't zoom in here. Oh, I see blank. No, you have to. This is the 1 point means here you have to zoom in. So like magnifying glass. And if you zoom in, zoom in, zoom in, you will get a straight line. Of course, without, we won't be using magnifying glass, but still it will represent a straight line. And hence it is differentiable. And here is this expression. So when you're looking for, is it differentiable at x is 2? And you just zoom in, yes, it will resemble a straight line. But when you look here, it won't. Because when you zoom in, it will just resemble a point. It won't look like a straight line. So this is not differentiable, we can say, like all the points, because at x is equal to 0, right? So the derivative fails to exist, or when you're checking for whether it's differentiable or not at a point. So if it's discontinuity like this, then it is derivative fails to exist. Discontinuity, the whole, the jump, the vertical, asymptote. So they say something like at these points, the derivative fails to exist. And some other examples are cusps and corner. Cusp means, so that is a turning point, kind of this, in a curvy manner. So when you focus here, when you zoom in here, it will represent a point, then a straight line. And here also, a sharp turn. Here also derivatives fails to exist, but still they are valid continuous functions, right? And also the next one is vertical tangent. We might think like, oh, when I focus here, I will get a straight line. So then it means it is differentiable one? No. So because at this point, when you have a vertical tangent, the slope is undefined. You can't say what is the slope over there. So in that case, this is it at this place also the derivative fails to exist. If you see a vertical tangent at a point, there also derivatives fails to exist. Right? A quick example. Identify points where derivatives doesn't exist. It's smooth, continuous. So you will be focusing on discontinuity. Here a jump. So x is -4. Here a corner. At x is 0, no derivative exists. And again a jump. So x is 2. These are the points derivatives does not exist. And so the final essence what we have did is continuous and differentiability. Every differentiable function should be continuous. But the reverse is not necessarily true. Sometimes it can be true. Sometimes it cannot be. So differentiable means it should be continuous. Then I will look for the like cusp or corner. We will remove that. Okay, they won't be differentiable. But converse, if it's a continuous function, then I have two choices. Okay, it can be differentiable or it cannot be. So this is the main thing. Now we are entering into the the derivative rules. So finding the derivative expression. First rule is applying the power rule. It's very simple. If your f of x is something like this, x power n, so you see, variable is in the base, exponent is a kind of a number. Then the derivative expression will follow this rule. You multiply the n in front and remove 1, exactly 1 from your exponent. That's simple. Now, applying power rule. Okay, so this is something you can express this in power form. For example, how to solve this? First, make in the convenient form, right? So x root x means x power 1, root x is x power half. You combine it and make it in the convenient form, like the simplify it as much as possible. Now it becomes like x power n. Now you apply the rule. F of x is x power 3 by 2 and apply the power rule. F dash of x is multiply this and subtract 1 and simplify it. And try to make always the expression is the simplified version. Without x power half, you can convert to root x. That's simple. Then derivative rules for constant, sum, difference, and constant multiple. Okay, what if I differentiate just a number? Yes, you can do. If c is just a number, derivating it with respect to x is 0. And sum or difference, for example, you got something like x plus y, like x plus sine x. So it's very simple. Differentiate the first part, plus or minus, differentiate the second part of the function. And constant multiple, like a constant and a function. So you take the constant out and apply the rule for that function of x alone. So these are the rules. And here we need to reiterate three things: horizontal tangent lines, equation of tangent and normal lines, differentiability of piecewise function. Let's go one by one. What is horizontal tangent lines? Okay, I will draw a tangent at a point, but I will get a horizontal line, which means the slope is 0. So horizontal lines have slope value 0. This is enough. And the how to find that horizontal equation means you find f dash of x and set f dash of x is 0. So the tangent lines will be horizontal for the zeros. When you solve for x, you will get some x values, right? At those x values, if you draw the tangent, it will be horizontal lines. A quick example: find x values where f of x have horizontal tangents. What's the first step? Find f dash of x. And you apply the power rule. It's very simple. 1 over 3. This will be multiply 3 in front and reduce on power minus 4. X is, when you derivate, it's just 1 because 1 into x power 0. And this is what we got. Then set f dash of x is 0 and solve for it. X minus 4 is 0 and factorize it properly. X squared is 4. This is very important. X is equal to plus or minus 2. It's not just 2. Okay, so we got it. At x is equal to 2 and minus 2, if you draw tangent lines, they will be horizontal. Then equation of tangent. Already we have seen equation of tangent line, right? So let's quickly reiterate it. So in place of y1, because at x is equal to a, if your function is f of x, this will be f of a. And slope will be f dash of a. That's simple. Now how to find equation of normal line? So this is my graph. And you're drawing a tangent line, right? So normal line means at a point you have to draw a tangent and your line should be perpendicular to the tangent. This is called normal line. So very simple. So the point will be a comma f of a, and it will be the same y minus f of a, and slope will have a change. For tangent, it's just f dash of a. But for normal, like the slopes are m1, m2 equal minus 1. Product of perpendicular lines and their slopes will be minus 1. So one slope is actually the perpendicular lines. One slope will be negative reciprocal of the other. So negative reciprocal. Reciprocal of f dash of a is 1 by f dash of a. That's the slope of normal line. So we have to change that. This is the only change. And x minus a. Right? So that's simple. Now find equation of tangent and normal lines of this function at x is 3. Very simple. Write f of x and find, because we need f of a and f dash of a. So f of 2, okay, this is actually 3. F of 3 is 1/3 of 3 cubed, which is simplified, it's 9. And find f dash of x, and f dash of 3 would be 9. Then equation of tangent line, we know the expression y minus f of a, right? F of 3, which is 9, equal the slope. Slope is this 9 times x minus 3. And simplify it. Then equation of normal line, it's same y minus 9 equal, the slope will be negative reciprocal. So minus 1 over 9 times x minus 3. And on simplifying this, you will get something like this. That's simple. Now differentiability of piecewise function analytically. So this is a function. Is it differentiable at x is 5? Of course, we can see there is a change. Okay, will that change be continuous? Like, is that differentiable at that point? Without graph, how can we do it? So first thing is continuity check. If it fails continuity, then no need to go further. It will be surely not differentiable. So I did something f a minus of 5, f plus of 5. I did mean this, since it's a piecewise, I'm taking continuity check for left of 5 and right of 5. Right? So we have to, for continuity, you just want to plug in the value in the function itself. So I'm just plugging in. For left of 5, take the first branch. Right of 5, take the second branch and plug in. I got a equal value, like they got verified. So it's continuous. Now we need to check for derivative exists at that point. Very simple. f left derivative and right derivative. So we have to find f of x, f dash of x for both the branches, and f left derivative of 5, f right derivative of 5. It's very simple. You just plug in, this is the left derivative, this right derivative, and simplify. They also got verified. They satisfied. And so its derivative exists. So which means, yes, the given function is differentiable at x is equal to 5. Okay, right. And next is derivatives of cos, sine, exponential, and logarithmic function. Derivative of cos x and sine x. Cos x, it's minus sine x. For sine x, it's plus cos x. So sine is important. We know sine and cosine, it's quite easy to connect, but sine. Cos will give a minus sine. Sine will give a positive cos. Okay. An exponential function, a power x, any base with power x, that allowed base, not 0, right? A power x will be copy the function and ln natural logarithm of the base. That's simple. Copy the function, ln of the base. Now for x, the special function, Euler's base, right? So copy the function e power x and ln the base is e. Ln e, they are inverse of each other, they will get cancelled. All right, ln e is just 1, so e power x. Derivatives of logarithmic function, d by dx log ax is you reciprocal of the input, 1 over x times 1 by ln of the base of the log. And if it's ln x, reciprocate the input, 1 by ln of the base. Base of ln is what? It means log e. So ln e. Ln e is 1, so this will completely become 1 and it's just 1 by x. Right? Now we have some other rules. The first rule we are going to see is product rule and then quotient. What if I get some function, for example, x root x we got, that is also product function, u1. You consider that as two different functions. Two functions connected with the product symbol is product function, and we can apply this rule. F dash of x is u dash v plus v dash u. So u is a function of x, v is also something, an expression of x. So simple, first you derivate u dash, then multiply second function as it is. Then it's a plus, derivative the second one and keep the first one as it is. That's simple. A quick example on this, log 5x cos x. So I have taken u as this and v as this. So find u dash, log 5x means reciprocate the input, 1 by ln of the base. That's it. V is cos x and it's negative sine x. Now apply the product rule and simplify it. That's simple. Now quotient rule is, what if I have like u by v function at the top and in the denominator? So this is something like u dash v minus v dash u by v square. So it's a minus and it's important. First derivative of numerator, denominator as it is, minus denominator derivative, numerator as it is, divided by v square. V square, not v dash square. And a simple example, ln x by x. My u is ln x, right? And v is, u dash is 1 by x. V is x, v dash is 1. And you write the quotient rule, apply it and simplify. This is the f dash of x using quotient rule. Now, finding the derivatives of tangent, cotangent, secant. These are other, right? So main function is sine, cos. So these are other, we can derive it from, if you know sine and cos well, then this is simple. So this is main. Derivative of tan x is secant square. We can even derivate it because tan x is sine x over cos x. So you can just apply u by v, quotient rule, and you will get secant square. And secant x is 1 by cos x. Again, you can apply u and v. U is this, v is this, and you will get this function. And this is also same. Cos x by sine x, apply u v rule. 1 by sine x, apply u by v rule. Right? So we can derivate. You can even memorize it, but it's quite easy to derivate it also. You can form it. If you forgot it, just go ahead with this. And you should be thorough with this. Derivative of cos and sine alone. Now, estimate the derivative of f of x, secant cube 5x at x is equal to 1 using calculator. Let me tell you. Because in calculator, we will only have sine and cos major, right? But I got secant means, you know the basic relation. Secant means 1 by cos, right? And also cubic function, sometimes we can't say. Still square, calculator will be having. So you have to modify this as the calculator accepted. For example, secant cube 5x means 1 by cos 5x the whole cube. In this way, you can give an input. You can't directly give this in some calculator. Let me show you. Yeah, you can even use Desmos, but let me explain you with calculator first. Okay, so we are going to go for calculus, numerical derivative at a point. Yeah, we are going to estimate the value at x is equal to 1. And yeah, first derivative. So d by dx of, actually, we have to go for secant cube, that one. So if you just give something like this, secant power 3 of 5x, some calculator we have that feature, but sometimes it will show some error. Yes, because it won't accept that cube, right? So in that case, we can just copy and do the alternate step. So in that case, what we will do? 1 by cos. So go for this fraction form. 1 by, first use the bracket and raise it to the cube. Then cos 5x and use the parenthesis. This way we can do. And we got something like this. At x is equal to 1, the derivative of this function is negative 2221.6. That's simple. Let me clarify the same example with Desmos here. Okay, first you just give the function. Here you can give secant 5x the whole cube itself. So this is a function. And then you write the expression f dash of x. At x is equal to 1, you need, right? X is equal to 1. Then we need to look for the connector point. So you just click over there. At 1, this is your f dash value. So it's same. Graphically and analytically with technology, we can solve like this. Hope it might be helpful. And that's the review that we have done in this video. I hope this video might be helpful. If yes, you can just like and share with your friends who is pursuing AP Calculus. And yeah, that's it for today. So thanks for watching. We will be meeting in another video with yet another interesting stuff. Until then, keep learning and keep practicing. Thank you.